why am I going to talk about something to do with magnetism and causality on a quantum optics conference? I'll get to that motivation in a little bit. First of all, a little bit of background. Who am I? Well, I'm Nick. I work at the University of Glasgow. And I do like to point this one out every now and again. You can quite easily spot the Glaswegian region on just a map of average rainfall. It's somewhere around there in the dark blue, as you can probably guess. You don't really go there for weather or anything like that. You go there because of the people, and I'm part of the quantum theory group, where you get to work with some of these lovely people. I think Sarah Croak and Steve Barnett are probably the most familiar to this sort of audience here. Right, so what am I going to talk about today? Well, I am going to talk about, we all seen plots like this, or rather graphics of this form in your undergraduate texts, really. So if you apply some magnetic field across some material, and sometimes the magnetization points in the opposite direction. So this is what we call diamagnetism. Right. So why on earth do we care? I'll get to that in a moment. Also, why there's an issue. Why am I talking about this? I'll also go down on how I'm actually supposed to resolve this. And this is work mostly together with Steve. Just so you know. And if you're more interested, there are some archive papers. I've looked at one contains more maths than the others. I'm presenting more the version here that contains the least amount of maths, don't you worry. So, okay, right. So why in quantum optics? Why would we care? Well, we really care about how do we produce and manipulate photons. And that's a big part we would just about gone to those in superconducting circuits. But yesterday, talking about placing atoms near materials, this is the bread and butter of quantum optics, really. And often this is done by materials. So I'm a theorist, right? So the atoms look something like that. You have some excited state, a ground state, and you get some emission. Okay. Place this in between two mirrors, we have your cavity QED system, right? This is all that sort of standard stuff. Or if you place it near some material, you can get couplings into material and back and forth. This is your usual Purcell effect. You usually get some sort of enhancement of the decay rates close to material, or close to material resonances, really, depending on how these things overlap. And this is really how I ran across this problem, was because if you look in the literature, you get this question of, what if this material is diamagnetic? It might sound like a bit of a silly question, but theoretical inconsistency here and everything like that. And turns out that the answer is we have no clue, which is a little bit of a problem, right? There's clearly something has gone wrong somewhere, right? It won't do, right? So then it begs the question of why? Why doesn't this work? What's the problem with diamagnetism and all this sort of stuff? And my title might have hinted something to do with it. It has to do with some inconsistency with causality. So there's a bit of a long-standing issue with this. For that, I do need to detour a little bit with some maths. Even if I'm sure most of you are gonna be familiar with this, this is probably the nicest way I have seen this explained. It's a paper from '58. I'll get to that in a moment. But we're going to talk about some response functions. So magnetization, you apply a magnetic field, whether you call it B or 8, it doesn't really matter. The problem is the same. And susceptibility, right? And then diamagnetism, as we usually talk about it, it's what's the zero frequency response here? And we want it to be less than 0, otherwise it would point in the same direction as your magnetic field. Cool, and that is the problem, right? So why is that a problem? Well, for that I need some assumptions. So usually when these theoretical inconsistencies come around, it has to do with the fact that you've broken some of your assumptions somewhere, right? So this one I care about quite a lot. Causality, if you do something, if you wiggle something, you're really going to get an effect later on in time, right? And that's a principle that we should care about. Reality, yes, okay, so the magnetization is something measurable, so we better have, it needs to be some sort of real field. And this one I will get to exactly what I mean with this, but in general, unless you are pumping the system, unless you're putting energy in, you can lose energy. You can't just spontaneously gain energy. Okay, so based on these three, my claim is that that shouldn't happen. Okay, so for that we need the ubiquitous Kramers-Kronig relations, and depending on how much lately you've been looking at complex analysis, they might stare at you immediately or not. But in essence, and again, this is this paper from 56, actually, not 58. This is one of the nicer explanations, at least I find, of this. So if you imagine a magnetic field or electric field or whatever, so you have caused some sort of source. This is time is pointing in the left-hand direction here, and you're emitting some sort of wave. And honestly, it doesn't really matter what system you talk about at the moment. So, okay, how Kramers-Kronig is about? It's about linking absorption and dispersion. So absorption, I'm gonna remove a frequency because I have a very, very narrow resonance here. So this is of course a pure sine wave or cosine wave, by the looks of it. Okay, so I remove this, and unsurprisingly, well, that equals that pulse minus this thing. Okay, that's acausal. I mean, so how do we deal with that? Well, the only option you really have is that you can fiddle a bit with the phases in between of your other frequencies present, right? That is the only way you have left to cancel this acausal bit. So that gives a sort of physical intuition of why is dispersion absorption linked. Again, the mathematics is there. It's been there since the 20s, or if you want to go all the way to complex analysis bit, late 1800s, I think, Sikorsky and Plemel did these things. So if you translate this, and this is theories, of course, so maths matter. You have your real part, and the exact form here doesn't really matter. The more important part is the zero frequency. And depending on how familiar you are with these things, the problem might stare you in the face, right? You have a reality really enforced that we have between 0 and infinity here. We are integrating positive frequencies. Integration sum, who cares? It's a principal value, but again, who cares? This here is a positive thing, and the passivity assumption there usually is translated into this being greater than 0 all the time. So this is greater than 0. Okay, that's a bit problematic for diamagnetism, because diamagnetism was the entire statement that this is less than 0. So, how do we deal with this? This sort of theory from the 20s really claims that, well, diamagnetism then ought to be impossible. Nature obviously disagrees. This, you can do these experiments. I can't, but you can put a magnetic field across. One of the more famous and funny ones are probably this from the 2000s, where they put a ridiculously strong magnetic field across a frog, because water is diamagnetic, and you can make the frog levitate. And I am sure it had a great time doing that. And this is some video from my undergraduate, where superconductor and you're playing with diamagnetism. This is a similar effect. It's slightly different physics, as I will get to, but diamagnetism is clearly an effect that sort of exists, right? I'm not the only one who have had this problem, come across this problem and wanted to have some resolution to it. There are a few. I don't have time to go through them all. They really come into slightly different types. Kramers-Kronig does not apply is one of them. So spatial dispersion and all that sort of stuff, nonlinearities are all problems. The one that I think is important to point out is, if you look in Landau and Lifshitz' book from the 60s, you see something along these lines. So the claim is that if we put an upper bound on this integral, so it's permeability instead of susceptibility, but whatever. Because the imaginary part at some high frequency ought to be 0. And hence this omega mu1 here doesn't have to quite obey the same laws. I mean, this is quite obviously a fudge. It's for one, if this is 0, well, then you can extend your integral to infinity. Secondly, there's a whole host of mathematical problems with doing this. But I think point goes to show that in the second edition, this doesn't appear. But I think Landau was one of the early people that sort of pointed out that this is an issue. So what's our resolution to this entire thing then? So how do you do this? And for that, you need to be a bit careful. I need to go back to how do you calculate susceptibilities and all this sort of stuff. And point out one of the crucial things is that up to E squared, so electric charge squared, all the transition operators, or all that sort of stuff appears twice. We're talking off-resident transitions here, right? So even though I'm talking static magnetic fields, that's the point of Kramers-Kronig, right? It relates all frequencies together. Something goes up, and then it must come down. That's a pretty generic principle. And in general, when we do this, we need to keep track of all the different, the multipolar orders or whatever expansion order we are doing. And in this particular case, it's the size of the atom. So we have something, the electric dipole, and if A is the size of your emitter sort of thing, wavelength here, next order comes electric dipole, electric quadrupole. I'm sure you're all familiar. You multiply by another order here, you get electric quadrupole, and electric octupole. And not an order people tend to care about, but I promise comes out to be important here. Because in particular, we need to keep something to A to the fourth, basically. So this is dipole, fine. But it's the magnetic dipole transition, which is your paramagnetic response, right? That comes off as A to the fourth. And of course, we all know that the electric quadrupole should be in there. Again, this is not something we usually care too much about, but it needs to be in there. But to that same order, you also have an electric dipole and electric octupole, which, believe you me, that calculating anything with electric octupoles are not fun. It's a fair amount of algebra, but you do need to keep it in there. So electric dipole, magnetic dipoles, and then we have the quadrupole, and they enter with some sort of spatial dispersion in there. So something like that. And if you naively go through, you calculate these things, you do your usual second order perturbation theory and throw this in, your permeability, permittivity, some resonances. This is your electric dipole transitions, and I've sort of gathered it together to make the maths look nice here. Not all of these are zero at the same time or non-zero at the same time, really. The important part here, you have the diamagnetic part, you have the paramagnetic part, they compete as usual. That minus sign is important for this entire resolution. And to explain that, well, for the electric dipole, this is always going to be positive. You go up, you go down, you always, with the electric dipole, get the conjugate to another, right? Magnetic dipole, the same thing. Electric quadrupole, really the same thing. Yes, you have a spatial derivative in there, but, all that sort of stuff. Electric dipole octupole, however, you do not. This is an interference effect. Dipole up or down, and then you're not necessarily canceling the k squared in there. Okay, these are not. I see that I'm slightly running out of time, so these are not quite satisfactory. There are, there's some things you have to obey to do with how you formulate these kind of theories. And for one, the interpretation is rather hard with spatial dispersion because you're no longer really quite sure about, because stuff like causality, it doesn't have the same interpretation when you're no longer local in space, right? So if you emit something here, if you have spatial locality, it doesn't translate quite as nicely as just something being emitted forward. Now, Maxwell's equations really only care about currents, so we can reshuffle things. And if we do it in this particular way, we put all the dipole stuff in your permittivity, and the permeability gets to eat up everything else. Then you're fine, basically. The resonances here are clearly all causal. This permeability, this has a, this has the correct competition between the diamagnetic stuff and the paramagnetic stuff. And causality is then satisfied. Oh, fantastic. So what did we break, right? Must have broken something. Otherwise, those three assumptions that led to my, inconsistency, something, right? And it turns out that around the electric dipole resonance, you can have the imaginary part of this chi, so the permeable chi, to be less than zero. However, your waves, you're still absorbing, so who cares, basically. This is really what you have to care about. You have to make sure that you're not, in general, gaining energy. So in other words, we kind of have to remember what Faraday and Maxwell taught us a good 150, 160 years ago, that magnetism and electricity really doesn't come by itself, even if we're talking statics. Okay, so what have I been talking about? Well, diamagnetism really has been long thought to be incompatible with causality. So this has really hindered how we deal with this theoretically in a quantum optics scale of placing atoms near emitters. The resolution, really, you have to keep all the way to the octopole. A little bit annoying, but whatever. And also the fact that you're electromagnetism rather than electric, electric or just magnetism by itself. Some predictions coming out of this that I really don't have time to go into. Well, first of all, we have new ways of manipulating these emitters and placing them in close to new types of materials. All good fun, and I'm looking forward to having some look at how these things behave. Now, because of some rules and how you make sure that you're theoretically consistent, there is now a link between the octopole response and the diamagnetic response. So these are algebraically linked to one another. And what I'll throw in there is that it also sort of explains the absence of dielectricity, so the electric analog of it. Have a look at the archive papers if you're interested. Should thank our funders, so the Royal Society and the Royal Commission for the exhibition of 1851. This is very British types of funding bodies, I have to say. And of course, Steve Barnett. With that, thank you for listening.
Do we have a question for the speaker?
Okay, I must have missed something fundamental about your logic. So, Kramer-Stronic relationships, they rely on linearity and causality, right?
Yep.
And then you have the right-hand side that's greater than 0 and the left-hand side that's less than 0.
Yep.
And then you invoke this argument about, magnetic octopole and quadrupole moments. What does it change? Does it remove causality or does it remove linearity?
So causality is preserved. Yes, this is important, right? The causality is preserved in this entire argument. All it really had to do with this, the passivity assumption being a bit too strict, really. And so let's go all the way back to blah, 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 blah. That this thing is always greater than 0. This is usually always greater than 0, but not if you're separating magnetic and electric fields. Then if you are in the magnetic susceptibility, you're allowed to be greater than 0, as long as your total wave is absorbed. That's the physical picture here.
Okay, let's thank the speaker again. Thank you very much.
Okay.